Here, the problem is, how do you find the connection between two variables when you have various pairs of values of them that have resulted from an experiment? Obviously not from a calculation, because if those were the results of a calculation, you'd have known the formula we were using in the first place. The problem here is, what is the formula? What is the connection between the result and the input number? Well, you have to start with some simple models. The two simple models would be, is it a power connection, is there a power involved, or is it linear? If it's linear, that means plotting these points, the answer against the input number would result in a straight line. And a straight line is perfect because I know straight away its form is going to be y equals mx plus c. And there's absolutely no doubt about a straight line. If it was a straight line, that would be perfect. But if it were a straight line, that means since I've got equal increments here, I should have the same increments in the answer, and I don't. So it's obviously not a straight line. So if it's a power one, what are the possible models? Well, the two possible models would be either it's a fixed power, and it could be something multiplying it, in which case its graph should look like this, and herein lies the problem. The basic graph of x squared, and again I'm only counting the positive parts of x, the graph of x squared would look like that. If I multiplied it by something, it would still look like this. There would just be a different scale. It might be skinnier, it might be wider. If it wasn't x squared, if it was x cubed, it would still look like this. And if there was a multiplying number, it could make it skinnier, it could make it wider. I can't tell what the power is. If that was the graph, I don't know what a is, and I don't know what n is. And it's worse than that. What if there is a power involved, but instead of a fixed power, so I've just got a simple power term, what if it's a variable power? So that it was something like a times some fixed number to a variable power. In other words, it's an exponential equation. Well, if it was an exponential connection between them, it would still look pretty similar to this one. Again, just taking the positive values. The only difference would be this, strictly speaking, should start at 0. If I've got any information down here at 0. And this one, the basic exponential graph starts at 1. So if I multiply it by something, it will start at that multiplying number. So that would appear then, you can distinguish between the two of these. Yes, if you've got the information round about 0. If you've just got some information further on that gives you a graph like this, I'm not sure whether it's a simple power term or whether it's an exponential term. Apart from one feature, that an exponential graph climbs much more rapidly than a power term. So the first thing we'll do here is draw the graph of this. Now this is it here. I'll plot those points more carefully. When x is 1, y was 4. When x is 2, you've got 22.6. When x is 3, it goes up to 62. When x is 4, it's 128. When x is 5, you're up at 223. You can see quite clearly it's climbing. That's not a straight line. It's a curve, so it probably involves some power. But what type is it? If you were to draw a line through the points, you can see that it's a curve, but I've not got the information about the origin here. So then we're going to have to say something like, well, is it y equals ax to the n, or is it y a b to the power x? Which of the two of these is it? Well, it's logarithms that will give me the answer to this, because logarithms are powers. If y is a fixed power of x, then the logarithm should be a fixed multiple of, well, in this case, the logarithm of x. So I should get a straight line. And it's when you've got straight lines that you know the equations for certain. So what I'll do is I'll take this form. What would happen to this if I took the logarithm of both sides? The obvious logarithm to do is base 10 in calculations. So if I take this one and take the log base 10, which I'll just write as log of both sides, I'd have this. The log of y should be the log of ax to the n. Then start using your laws of logs to split those terms up. The logarithm of a product is the same as the individual logarithms added of the two factors. Then, when you have the logarithm of a term involving a power, the handy thing is that power can pop out. So I've got log 10a plus n times log 10 of x. And then rearranging that, I've got log 10 of y should be n times, remember n was that power, log 10 of x plus log 10 of some fixed number. Now that's in the form of a linear equation. That's like the y coordinate, the gradient, the x coordinate, and some fixed number, the intercept. In other words, if that was the connection, and I was to plot, instead of x against y, I was to plot the log of x against the log of y, I should end up with a straight line, and the gradient of that straight line should be the power that's involved, and the intercept, if you know it, would give you the value of the multiple. If it were the other one, if I start with y equals a times b to the x and take the logs of both sides, same principle would apply. I've got a product, so I can separate them into the sum of the logarithms of the two factors that make up that product. And when I've got a power, I can pop that out, so I've got x times log base 10 of b. So again, I've got log y equals, but this time it's log b, which is the power, which will give the power x plus log 10 of a, which is again a linear graph, a linear equation. But if I was to draw the graph of this, it'd only be linear if I drew log 10y against just x. Then it would be a straight line, where the intercept would be log 10a and the gradient would be log 10b, from which you get the base of the power. If I was to draw that instead against the log of x instead of just x, well, the log of x is going to compress it, so instead of being a straight line, with that being compressed, and of course it's not linear, if that was 10, then that would be 100, and that would be 1,000 in terms of a log graph. So instead of a straight line, that should again just produce a curve. So I can tell which one it is. If it's a proper power term, log against log will give a straight line. If it's an exponential term, log against log will still give me a curve. So let's get the logarithms then and see what's happening with this. So what's log 10 of x and log 10 of y? So there are the logarithms then. Plot them in a graph. Here's the graph. Log 10 of y against the log 10 of x. Plotting those points, I'll just highlight them more clearly. 0, because log of 1, no matter what the base is, log of 1 is 0, because it's power 0 that gives a 1. Logarithms are powers. 0.3, that would give it that 1. 0.477 goes there. 0.6 goes here. And 0.69 goes there. And they quite clearly lie in a straight line. Like this, which means for this particular one, I know that this is the connection. It's a simple power term, not an exponential term. And now it's just a case of how exactly will I find the multiple and the power? Well, there's two ways. If you've got the log data already, then you can just use your log data to find these numbers just by using that equation. Oops, did I forget that VA? So I've got n, the power, will be the gradient of this. So I can just write down, n is going to be the gradient. And you'll get the gradient just by taking the difference between any 2 points. So gradient, difference in any 2. So that's going to be the difference in the y's over the difference in the x's. But of course that's the difference in the logs of y, the difference in the logs of x's. I could say this, it's the difference in log y over the difference in log x, just to save writing log y2 minus log y1, etc. So what have I got for this then? Just using these first bits, I've got 1.355 minus 0.602 over 0.301 minus 0. That's 0.753 over 0.301, and when you put it into a calculator, you get 2.501. But remembering that not only was that data from an experiment, but the logs have been rounded off considerably, then this won't be completely accurate, so you would shorten it a bit to something a bit more convenient like 2.5. That seems a bit handier. So the power in that should have been 2.5. The next part would have been this. How do you find what A is? Well, since I happen to know where it cuts the vertical axis, I can just read that from the axis then. I've got that log 10 of A was, when the log was 0 for this one, for log x was 0, is 0.602, which means that removing log base 10 makes it the exponential on the other side, 10 to the power 0.602, so A is going to be 4. And there's my connection. Y equals 4x to the power 2.5 was the formula that connected x and y in this particular case. Now, if I didn't have the convenience of having this x equals 1, so this log x equals 0, so having this intercept, if I didn't have that luxury and those points weren't there, then what would be this procedure to find this equation? We know it's in that form because I've got a straight line for log against log, so it is simply a power one. Well, I'll just go through the same process here. I'll get the gradient, but this time I'll have to use two other points, and then in general, even though these points all lay exactly on the line, they might be scattered, and of course you wouldn't have that first one. So you'd pick two good points on it, and then use those two good points to work out n and a. So I would do this for the first part, say gradient. Well, let's just take the first and the last point. So difference in the logs. 2.349 minus 1.355. That's the difference in the verticals. X's, or rather log x's, 0.699 minus 0.301 for the difference horizontally, and the gradient will be the vertical over the horizontal. A little calculation, not much different from before. Doing the subtraction, 0.994. Lower one, 0.398. Dividing that out, you would get 2.497. And again, realising that these are being approximated, I'd shorten that off to something convenient. So I'd have n equals 2.5 as before. Well, that wasn't much different from working at the gradient when I had these nice little points. It all depends what I've got. If I've only got this data here, and I don't have the original data, then I'd have to substitute it back into this equation. If I did have the original data, then putting 2.5 in, I could simply put in the raw x and y and find a. So I'm just taking this all from the log data. If that's all the information that was given to me, so if you had this question in the higher, for instance, and it said it's suspected that something has a connection in this form, the logs of some values have been worked out, they form a straight line, so you can form this equation here, and then from this data find it. This is the way I'd have to do it. So I'd get the gradient from those numbers, and then to find this a, I'd have to substitute it back into here, because this equation now reads log y is 2.5. I know what n is. It's 2.5 log x plus log a. So it's only log a that I don't know. But those are the variables, and I've got loads of values for them. I've got 2.5 now, so that's the only unknown. So you could put any of those points into it. So say I just put the first one in. When log 10y is 1.355, log 10x is 0.301. And then the only unknown is the log a. So I could rearrange that. Log 10 of a is going to be, if you multiply that and take it across and subtract, just to save a bit of space, you get 0.6025. And then a is going to be, get rid of log 10 by doing its inverse, exponential base 10. Pop it into the calculator, you get 4.004, so a is 4. So you get the same results before. Y equals 4, x to the power 2.5. Now, If the problem started with the connection between them is some fixed power relationship, so you knew it wasn't exponential, and you didn't have the values for the logs, instead of working out the values of the logs and then substituting them into the log equation, you could just solve this directly by putting in the values of x and y, the raw values, and get some simultaneous equations and solve them. It may well be that you could have something in the question that says, show that the logarithms would form a linear graph to demonstrate that it is a fixed power, just as I had at the beginning of the video. So assuming that that part was done, and it was just a case of, here's the connection with a fixed power, here's the raw data, what's the value of a and n, I would just pick out pairs of values. Again, I've got this luxury here of this 1. That's very convenient, because I could pop those in. I could say, well, when x is 1, y is 4, and the handy thing about that is 1 to the power of anything is just 1, so straight away I would get a is 4. And then once I know that a is 4, my equation now reads y equals 4x to the n. And I could pop in another pair of values, like the second pair. So I've got 22.627 equals 4 times 2 to the power n. Rearranging that, 2 to the power n would be 22.627 divided by the 4. So 2 to the power n would be 5.656. And then to find n, well, all depends what you'd be allowed to do. Just to get rid of the 2 straight away, I would have, well, n is, opposite of the exponential would be log base 2. And your calculator may well have log base 2 in it if you're allowed to use it. Log base 2 of 5.656. Now, log of any base would be this button here that's got the various parts in it. You press that and you can enter the base 2 and then put in the number 5.656 equals 2.499.
Well, careless, that should be 0.499.
Which you then round off to 2.5. Or if you didn't have or weren't able to use the luxury of log base 2, at that point I would say, well, if 2 to the n is 5.656 and I can't use log base 2, but I can use log base 10 or log e, use log base 10, I could take log base 10 of both sides. So log base 10 of that, log base 10 of that. Whoops. The handy thing about taking log base 10, maybe I'll just emphasise it here, is that power can pop out. N times log base 10 of 2 will be log base 10 of 5.656. So n will be log base 10 of 5.656 divided by log base 10 of 2. And you just pop that into a calculator. Remember to close all brackets and so on so you don't get an error coming up. And when you do that, you get 2.4997 and so on, which again you would round off to, conveniently, n equals 2.5. So there, you've got the two parts. A was 4, n was 2.5, so y equals 4x to the 2.5. Now, yes, it goes on and on and on. Now, if you didn't have the luxury of that 1 for x, which of course simplified this considerably, as it simplified the log 1, so I just had some other points, then I would still set out simultaneous equations, except I wouldn't have that convenient first one. What I would have in this case would be, using the first one, I would have when y is 22.627, that came from a times 2 to the power n, call that equation 1. Picking some other one, may well be the first and the last, it all depends which points lay best in the graph. To get 223.607, I would have had a times 5 to the power n. Now I've got two simultaneous equations. Two equations that have to be satisfied by the same values of a and n. And the technique here isn't a substitution or an elimination. What I'll do here is, I'm going to divide the equations. Same as you do in those wave function ones. I'm going to do 2 divided by 1. Which means that, if I put it on this side here, I would have a times 5 to the n over a times 2 to the n will give the same result as 223.607 divided by 22.627. The handy thing being, if you divide the equations, the a's will cancel out. And that n being the same power of those will just appear once. That's the same as 5 upon 2 to the power n. So 5 upon 2 to the power n will be this thing. And this thing divides out to 9.882. Same as before. Now, I don't have log base, and that's 2.5, so I'll have to take the logs of both sides. So what I'll do is I'll take log base 10 of that 2.5 to the n. I'll take log base 10 of the 9.882. That means I can pop that power out. And then finally divide them. So log base 10 of 9.882 divided by log base 10 of 2.5, finally giving me, which rounds off to 2.5. I've still to find what a is, but having found n, I can pop into one of those, like equation 1, and then just rewrite that. So I've got 22.627 will be a times, and it's 2, that's what x is, to the power 2.5. Now those are just numbers. So all I've got to do is take that number across and divide. So a will be 22.627 divided by 2 to the power 2.5, which I didn't even bother to work out here. I just put that into my calculator, use that fraction button, and the denominator will have 2 to the power 2.5, and you get 3.999, etc. So a equals 4. So as before, y equals 4x to the 2.5. So there's the two methods then, depending on the information you've got. Have you got the original data to find the form, in which case you can do substitutions. You may have an extra part, of course, that says show that if you take the logarithms of both sides, forms a linear equation. Or do you have the logarithmic data for that? In which case you would have to take that down to the logarithmic linear equation and substitute that data in instead. Now what about the other type? What happens if the connection between them, and you can see it's not linear here because those are equal increments but those aren't. What happens in the connection between them is a variable power rather than a fixed power. What if the connection between them is something of the form of a times some fixed base but a variable power? In other words, an exponential equation. Let's just draw a graph of that and see what the difference is. So here's the graph. We'll just highlight it again. At 1 it was 20, then goes to 80, 320. It's increasing much more rapidly. Notice that's a different shape of curve. But again, that's difficult to distinguish when you've just got the data for a few points. So that in this case, the graph's starting off slowly, then shoots off rapidly, an exponential growth. But again, it's difficult to determine the difference between the two power types because both look like curves, especially if you don't have the information about the origin, and I don't here. I don't know where it starts. Remember, one of the crucial differences was if it was a fixed power, it should be going through the origin. If it's an exponential, if it's a variable power, it should start at 1 or whatever the multiple is. But you wouldn't be able to distinguish that in a graph that doesn't reach the origin. Well, the next step would be, well, what about logarithms? What if I plot the log of x against the log of y? Well, there it is, changed into log base 10 of both of the variables, and the graph of that looks like this. Plotting that again, we've got that convenience of the ones and the zeros. Log base anything of 1 is 0. That's always a very handy point to have. Plotting those gives you this, which you notice isn't a straight line. So there's no linear connection between them, and it's only linear connections that you can identify straight away. In this case, I've still got a curve, so that connection was no use. And you could have got that simply by rearranging this using logs. I did it before in the other one, I'll just do it again here. If you take the log of both sides, I'll just use log to stand for log base 10. If you take the logs of both sides, I can use the law of logs to split that product into two sums, into the sum of two parts rather. And then the power in the log term can come to the front, giving me x times log base 10 of b, which I'll just write the other way around as log base 10 of b times x plus log base 10 of a. Now, that is a linear relationship. That's like y equals mx plus c, where the vertical variable should be log 10 of y, as it was here, but the horizontal variable shouldn't have been log base 10, it should just have been x. So it's another graph I need to verify this. Here, if I plot log 10y against just x, I get these values. Which are dotted about a little bit because these are approximations. I've had to round them off. I've got the original x against the log of y, so I'm ignoring this line here. Now that's a straight line, which means I can find the two parameters of it. What's its gradient and what's the constant? Not directly where does it cut the vertical axis, but I can do that by a substitution. So log 10b, let's call that log b, will be the gradient. So that will be the difference in the vertical variables, which is log 10y, just call that log y, over the difference in the horizontal variable, which is just x in this case. Picking these 2 points here, I'll have difference in those will be 1.903 minus 1.301 over 2 take away 1, which is very handy in this case because 2 take away 1 is 1, so that's 0.602 over 1, which I won't write because over 1 is just what it says. So if that's what log base 10 of b is, then b will be 10 to the power of that. And 10 to the power of 0.602 comes out as 3.99, etc., which we'll have to round off to 4, remembering that it was just experimental data, or that the logarithms have been rounded off so it's no longer completely accurate. And of course, if I didn't have my 120, my 1.301 in this case, it wouldn't be that much simplified because using any 2 points are going to involve the same amount of calculation. And then how do I find log base a? Now, I don't have the y-intercept, the vertical intercept here, so I'll just have to substitute it into the equation. So my equation now reads this. Log 10 of y equals, now that's not 4, that's still log 10 of b, so that's still 0.602 times just x plus log 10 of a. Popping in a pair of values. Now obviously it is easier using this because x is 1, but it wouldn't be much more cumbersome to use one of the other ones because I'd just be a 2, 3, 4 or 5. I will use this one in this case, but you could use any of them. So using this pair, x and this log, I've got 1.301 equals 0.602 times 1 handily, but it wouldn't be much worse if it was 2 or 3 or 4, plus log 10 of a. So it's only one thing I don't know, so I can find it. So log 10 of a, maybe I'll emphasise it here, will be 1.301 take away 0.602, which is 0.699, and then remove the logarithm by applying its inverse exponential. That'll be 10 to the power 0.699, and 10 to the power 0.699 would give me 5.0003, etc. But again, realising that this is approximate, I take that down to a nice convenient number, 5.0 or just 5. So my connection is y equals 5 times 4 to the power x for the exponential equation. Or, same as before, what if you didn't have the logarithmic data and you were told that there was a connection between the two of them in an exponential form, in that there's a variable power and you had to find the value of those two parameters, the multiple and the fixed base. and you've just got the original data. The first part may involve show there's a linear connection between the logarithm of y and just x. You could have that part to begin with, so you'd end up with the same expression as before. You'd end up with log 10 of y would be log 10 of b x plus log 10 of a. But then, without needing to work out the logarithms, you could find a and b by just using the original raw data in substitutions. And again, in this case, it's very handy to have x equals 1. So in this first part, if I do a substitution using 1 and 20, I would have this. When y is 20, I'll have a times b to the power 1. So that just says I've got ab equals 20. There's one equation. Using the next one, 80 is a times b to the power 2. So that means I've got ab squared equals 80. And the same as in the other technique, dividing the terms will knock out the a's here. So if I do 2 divided by 1, I'll have ab squared over ab equals 80 over 20. The a's will cancel out. The b to the power 1 will knock out one of those, just leaving me b equals 4. And knowing that b equals 4, I could go back to my first equation. I could go back to number 1, because number 1 is now going to say that a times 4 equals 20. So a is going to be 20 divided by 4, so a is going to be 5. Give me the connection. Y is 5 times 4 to the power x as before. It's much quicker in this case compared to the graph with the fixed powers. And as before, if I didn't have the convenience of that 1, and I just have some even more awkward numbers here, then I would just use any 2 points, same as before. I don't have the log data, I've got the original data, but I can just use substitutions. So I'd probably pick these 2 points here, but depending on the graph of it, which points fitted the best. So I'd have, as before, I'd have 80 equals a times b squared. There's one equation. 5120 equals a times b to the 5. There's another equation. The technique with these power equations is to divide them. That way the constants will divide out and so on. So that I'll have a b to the 5 over a b squared equals 5120 over 80. I just put the larger one on top, this one over that one. The a's will cancel, and no matter how nasty these numbers might be, how nasty these powers are, it'll simply be b to whatever the difference between them is. If you're dividing the terms, you subtract the indices. In this case, it turns out to be a nice little 3. Dividing that part gives me 64. And then that's not an exponential equation, that's a simple power term. So the opposite, the inverse of cube, is cube root. Cube root of 64 is 4. As before, you get b equals 4, and then just substitute it back into 1, same way as before. So 80 equals a times, and now we know that's 4 to the power 2, that's 16. 80 over 16, and that's going to be 5. Same answer as before, y equals 5 times 4 to the power x. There, that took ages. So the thing for you to do would be go back to the original data that was there and try that yourself.